Hey everybody, how's everyone doing today? So you've made it. All of us are here, and guess who actually made it to the show? That's
It's
right.
me.
One and only Daniel's here. Hi Daniel, how you doing?
Hey guys, I've been doing good. Been busy. What's the phrase? Busier than a one-legged man in a kicking contest. Um, but it's busier. Yeah, that's the name of the game nowadays. Everything is changing, and I've been working from home. There's been a lot of IT and tech stuff. Man, I've been up to my eyeballs in work, but it's nice to be able to just stop and do some 3D printing fun stuff once in a while, huh?
Exactly, especially with all the new printers that are coming out and all the new technology they're bringing out. 32-bit boards seem to be starting to come out with the major 3D printing companies, which I'm happy to see. I have a 32-bit board coming my way also. I won a board from TH3D. So I have their Easy board.
Easy board.
Yeah, so you can actually
look that up. I think there have been so many new tech offerings out recently. I can't keep them all straight. So the Easy board, is that the one with the trinamic drivers and it's a drop-in for the Creality?
Correct.
Okay, that's that one. I have that bookmarked here. Let me take a look at it.
Yeah, it's actually a very interesting board, the way that you set it up, that you can actually configure it online and then have it download the batch, which kind of makes it a lot easier for the people that don't know how to use the what is it now, VB I think it is, or just trying to remember what language is written in now. The 2.0 is Marlin.
Yeah, it's C-ish.
Yeah.
I don't know what it exactly is. All I know is how to configure it, and that's been enough for me. So yeah, other more technically inclined people like my brother, they dive in and try and figure out all this theoretical stuff about the language. I asked him if he could look through some firmware stuff that I've been monkeying with for sequential homing, and he's like, well, what language is it? I'm like, I don't know. It's C-ish. That's what the syntax is like. I mean, if you can read pseudocode, you can do this.
So let's go talk about C, according to Mr. Spectrum, because he went C sharp.
Okay. C sharp. All right.
I guess.
Looks good.
Yeah. So why do we bring this back? Because we actually got a question here. This was left by Ralph Hay 2 weeks ago, back on the stream that we're talking about 3D lead screws.
Yeah, that topic keeps coming up.
Yeah.
It seems to be pretty popular for some reason. People keep asking that, and whenever it comes up in the videos, it gets a whole bunch of questions.
Yeah, so this one's kind of interesting, and I kind of looked at it and really don't know how to answer it back. And I know that you may have looked at it, but just to let everyone know, you said, how is the Helical Coupler worse than a spider coupler? It appears that the helicopter still allows angular misalignments in a similar way that the spider does. I find that all metal construction of the helicopter to have advances over the spider for temperature heat chambers, 300 degrees Celsius, working temps. And I would like to understand the differences.
Right. So he's got a really good point right there. So a helical coupler, remember, those are the ones that everything used to have a little while back. They're just aluminum. They're slotted. They've got this kind of spiral corkscrew thing. So they look like a spring. You can bounce them. Those were, let's see. That's what shipped on a lot of printer bots. My printer bot Simple Metal. First printer I ever got had one of those on it. I was like, oh, this is just how these things work. And started looking more into the role of the coupler and what it's really trying to do mechanically in the whole assembly, and realized, no, there are other tools, other pieces that can fill this role maybe a little better without some of the side effects that we're not liking. So helical couplers have a couple nice things about them. One, they're pretty cheap. Two, if they're machined out of one solid piece, usually they run out, and everything like that can be tolerable. You slap them in and you hit go, and things are usually pretty centered on startup. The thing that we don't like about them is the fact that they are well, two things. They are gritty, meaning if you have any, not just angular misalignment, but you actually have like positional misalignment. We don't run into this much in printers with the top of the lead screw left open, but if you've got a bearing on the top, you'll run into this where the top 2 points constrain the bottom one to wiggle around. And if it does that, you're going to have stick slip artifacts as the lead screw engages and disengages from the surface on the motor shaft top. Now, one way to get around that that I've heard a lot about but haven't actually tried is you put a ball bearing in between the two. That way, so you got your motor shaft, you stick a ball bearing in there, and you put your lead screw on it, and you tighten down, and that way it replaces the grinding with rolling friction. I think that's pretty cool. That might be a way to get around this. The only other way to get around that is to leave it floating, but then it's bouncy. And actually, I had the printer set up like that for a while, and that's not a recipe for consistent layer registration. So, I mean, it can work if your axis is really well lubricated, but it's not great.
Yeah, I'm just thinking about the lead screw also. If you were to do that, I would feel that, you wouldn't have a level playfield either, wouldn't you?
Mm-hmm.
So your lead screw could actually not properly do the, well, I'm thinking to myself, like if it's NEMA 17, you got 100 rates, but if that, if it's not tied down properly or it slips, would be my concern also with having a ball bearing in there.
Right. Well, that actually brings me to another thing. So there are multiple different ways of clamping in these couplers. So in most helical couplers, you notice you've got set screws, often 2 of them, and 90 degrees from each other. And in professionally made couplers, that's a pretty good way to do things because you're going to have a really tight fit in the bore to begin with. It's going to be pretty much centered, and the set screw just fastens it. Now, in cheaply made stuff where the tolerances are loose, they have to oversize it in order to ensure that the tolerance range won't get below the diameter of whatever you're trying to fit it onto. That means that when you fasten the set screws, if there's enough of the tolerance mismatch, you're actually going to get an off-center jam. So that's the other thing about them. Now, I didn't touch on the other thing about helical couplers. I'll get back to that in a second. Spider couplers have one main disadvantage, and that's the elastomers can, under a lot of heat, get soft and gushy, and that would be bad. But we don't see these heats unless you're dealing with a really crazy printer. It's enclosed and it does got a chamber heater and all sorts of stuff.
If I was going with a chamber heater, I would probably stay away from a Spider.
I would probably too, just because they're preloaded. The Spider is oversized and it mashes up against both sides, so it's not like there's any just bouncy backlash. It's not like it's it's got some slop in it, but it does get softer as the temp goes up. So instead, I would probably just use a straight like lead screw integrated motor, where it just goes through the core of the rotor.
Oh, you mean like buy one that already has a lead screw inserted in NEMA 17?
Yeah, I'd probably do that instead in a high temp printer.
Well, that makes more sense.
Yeah, spider couplers have one nice thing that I really like above helical couplers, which is kind of the main reason I choose them now. If an axis, this is just kind of a fail-safe. If an axis goes too far the z-axis goes too far in the down direction, and it bottoms out on something, maybe because the Z sensor, whether it be an inductor probe or a micro switch, something isn't working, isn't wired correctly, or is missing its flag. Maybe the inductor probe was off the edge of the bed, or maybe the micro switch missed its the tab that's supposed to hit it. This actually happened to me a couple weeks ago with the Fred's printer. He had just got it and was trying to, get things up and running as fast as possible. It's like, oh, wait a minute. And the lead screw kept trying to climb through the nuts, but the motor stayed down there. So it stretched the helical coupler out like a spring, doing, and the helical coupler stretched to like double its height, all spaced out, nasty. So they had to go put it in a vise and try and mash it back together. It wasn't really great, but so I think they're going to try and replace that with a spider coupler. A spider coupler in that situation will just harmlessly disengage. The two halves will back out from each other, and then no harm done. So it won't actually wreck the component or continue transmitting torque. It'll disengage, and then everything's fine. So that's one thing I kind of like about those. Mr. Buttram is mentioning a blast from the past. The original Prusa used clear plastic tubing. Yes, a lot of old rep wraps back in the days of threaded rods. They'd use like an M5 threaded rod by 0.8 or 0.1, sorry, 0.8 or 1 millimeter pitch. Not a lead screw, mind you, just a threaded rod, and you'd have nuts, ordinary nuts, just an M5 nut as your lead screw nut. And needless to say, the tolerances on that setup weren't great, but they are good enough to print with. And in the nature, or in the, man, it's been a long day. What's the word I'm looking for here? In the spirit, there we go. In the spirit of a rep strap, where people are trying to pick their printers up by the bootstraps and get it running out of whatever materials they have lying around. Somebody figured out that you could take a coupler, or you could make a coupler out of a little piece of clear plastic tubing that was just the right size, 5 millimeters or a little less, and slip fit it over the tube, maybe put a ball bearing in the middle, often zip tie it to clamp it to both the motor and the screw. And that would be a decent enough coupler. It was very flexible, and it would be able to take out all the angular and radial misalignment. So yeah, it did work, but those often had a little bit more radial play. So
yeah. That's what I would think. I wouldn't trust that personally. But.
Yeah, I don't know if I would either. But they did work within their environment. They did what they were supposed to do. Now, of course, we're machining, or we're building printers with more machine parts and more reliance on conventional manufacturing techniques and machine design.
Yeah.
So most printers nowadays are shipping with like proper couplers that you get from somewhere. Although, like another person said in the chat, I think Barrett said most are shipping with solid couplers. And yes, that is something I've seen a lot more of recently too. I'm not sure why, but solid couplers are an interesting choice.
Yeah, I've seen it, like the Ender 3 is a very good example for that solid coupler, which I still am debating on switching over to a spider coupler.
Mm-hmm. So solid couplers come in two varieties that I've seen. One, the cheaper variety has the set screw issue we mentioned earlier, where if the bore is too big, the lead screw goes in off center, or the motor shaft, and the set screws will pin it off to one side, and now you've got axial run out. That's a little bit of a deal if you've got a flexible coupler, but in a solid coupler, it's a big no-no because you're forcing it to rigidly have misalignment, and that will cause Z-wobble. Not like might, it will. So the other type of coupler fastening system is a little better here, and this is where you have a split clamp. You've seen that type, where it's got two halves that are round-ish, depending on the level of machining, right? Nothing's perfectly round. Remember, everything here has tolerances to it,
especially with Chinese.
They're fairly round, and you just clamp them down. Yeah, especially when they're turned out as fast as they can on a screw machine. You clamp them down, and those tend to find center pretty well, even if the bore is oversized or undersized or any relatively close. You can mash it in there and you can jam it down, and it'll be more centered than it often is with the set screws. So I'm happy to see that. Now, spider couplers usually come with that, and that's a good thing.
Sorry, I just got a message here. I was just researching if it was worth bringing it or not.
Yeah, 3D printing instructor says if everything is perfectly aligned, solid works fine. Yes. So here's a situation where solid is actually a good thing, and not only solid couplers, but the type of lead screw integrated motor that we talked about earlier is kind of like a solid coupler motor. So if you've got like a brand name lead screw or even ball screw, something with actual documented run out specs, straightness specs, all that, and you've got a matching nut, a nut that actually like fits it tightly, and you've got a straight spot for it that's parallel to your Z linear rails or rods or whatever you're using, your Z motion components, and you have it all squared and trued and aligned, and everything is totally ortholinear and you can put a ball bearing on the top of that. You can have a solid coupler at the bottom. You won't have any problems. It won't give you any Z wobble. In fact, it'll be really nice and rigid, really responsive, and it'll behave very, very well. Now, most of us aren't building printers with $200 lead screws, and linear rails in that price range as well. Most of us are trying to do it with the less expensive, kind of mass-produced Chinese stuff. Chinese or not, tolerances or tolerances, wherever it's made is incidental. It's just a lot of these happen to come from China. Is the stereotype of where these printed parts are coming from. So in that situation, you're kind of setting the printer up for failure if you're trying to ask a lead screw with some bend, with some run out, with some slop in it, and you're trying to press gang it into service in a role that really only a high quality, high spec one would work in. So in that case, often it's a good idea to just accept that there are going to be issues with the lead screw, and instead use the constraint theory method of not over constraining the screw and just accepting that there's going to be a little wobble. Let it express itself out the top, and then it won't show up as Z wobble in your print.
Yeah. Just let you guys know that if you have any questions for Daniel, don't forget, look at this, read this here. Message me I'm going to be keeping an eye on the chat so I can always bring anyone in. If you got a question, let me know. I'll send you the link so you guys can come in through the StreamYard link and ask the question in person if you wish. So that is an option that you have available. Sorry about that, Daniel. Didn't mean to cut you off.
Yep, no, that's good.
So I got a question for you then. So if I'm changing the lead screw and I'm going, say, to from a 4-stop to a 2-stop, I guess it's a 1-stop or a 2-stop. It's 2-stop, isn't it?
Well, what
that means one start.
What
one
sort
start.
of lead screw do you have in it right now, and what are you trying to change to? Let's go in terms of that.
Okay. Well, no, let's say I'm building a new printer.
Oh, a new printer. Okay.
Okay.
Right. If you've got a new printer and it's a clean slate, you can choose any kind of screw you want. You can choose any kind of specs you want, any kind of price point, any kind of size. You've got no constraints right now. You want to build it around the screw. You've got a couple different options. You can go with lead screws, which use sliding friction, and you can go with ball screws, which use rolling friction. There are other weird things in between that are usually used for heavier loads, but those are the two main classes of screws. Now, in the lead screw camp of things, just like screws, fastening screws, I'm not really including those. Those are a different thread profile. They're meant for like statically holding in tension, do things together. They're not meant for power transmission or position transmission. So lead screws are usually made with very conscientiously picked, like a trapezoidal profile or some other profiles to them. There are some really neat screw profiles that IGUS uses. They have polymer self-lubricating nuts that they're really proud of, and they design all their lead screws around those. Maybe almost all of them, but that's kind of their claim to fame, is they have some really neat polymers. So they have some screw profiles that have these kind of curvy shapes. They're not trapezoidal like Acme, like we're all used to, like the TR8x8. They've got some funkier stuff. But those aside, most of the lead screws that we see are these trapezoidal profile, or they've either got like a 60-degree angle or something similar to that. And they'll often have a brass nut, maybe polymer, maybe Delrin. Delrin is really low friction on metal, and low wear. So you can run it up and down that rod a whole bunch of times and it doesn't like grind and turn into dust.
Yeah, it doesn't have any friction issues.
Yeah. So actually, can I do some screen sharing? Let me grab a model. I've got something really neat to show you.
Okay.
So
as soon as you share it with me, I can pop it up on the screen.
Yeah. I've got to find, I don't even know where it is. I got to search here. That's not the one. That's close though. Let's see here. All right.
Oh yeah, the humming of the computer.
Yeah, you hear him. All right, here he is. I found it. This is
Okay.
cool. This is something I was thinking about today. Like, yeah, this would be fun to touch on in the show. Let me just check the chat. I want to make sure no one's asking questions.
They're just posting. Barrett mentioned this here. He says the Voodon or Trudon did away with threaded rods. They use Z. They use belts for Z.
Nothing a metric hammer can't fix. Yes, yeah, you got to make sure you're using the metric one. These machines are metric, and if you use an imperial hammer on them, you will have all sorts of issues. I don't agree. Like you got to have the metric span wrenches too, the metric screwdrivers, the flathead especially.
Everything metric.
Along with the left-handed screwdrivers and all sorts of good jokes there. But
yeah.
Barrett mentioned something before I jump into this lead screw thing. I want to get to all the questions in here. He's noticed that on AliExpress, a lot of the Chinese printers have bearing top mounts with fixed bearings now. And the ones with play have vanished. Yeah, I don't know why that is. They kind of come and go. I've seen waves of it, like where they'll design a batch of printers with fixed bearings up there. They're like, no, that causes Z-wobble. And then they design it like for a year or two, they'll have them without it. And it's like, okay, that works. And then people complain about the lead screws rolling around. They say, oh, you know what we should do is throw a bearing up there. And they do. And now it looks good, but then the prints don't look good because the Z-wobble is transferred to the carriages.
So you're just saying if you got some wobble, probably get rid of the bearing altogether, right?
Yeah.
Yeah.
If the lead screw is tighter in straightness than the amount of lateral plate in the nut, then you're good to go. You can put a bearing on top because any play inside the nut side to side will just be allowed. It'll float.
Yeah.
The only issue that arises is if your lead screw straightness is greater than that, and it will push the side of the nut, point. That's when you get Z-wobble. It's dragging your nut around in circles like this. If it's just circling around very slightly, like a micron or two, whatever, nobody will know. It'll work great.
Yeah, something like the CR10, I know they put one on the top, but not a bearing. They just leave the hole open. Which I thought was kind of interesting concept to do.
Let's see what else we got. Voron and Trudon do away with threaded rods, use belts for Z. Yes, that's a whole nother discussion we can go into.
Yeah.
We'll get into that in a bit because that's another cool one, but not right now. We'll get into that a little later. See more POM nuts for lead screws too. Yeah, and I like seeing the polymer nuts. Brass is, it's okay, but polymer often in the versions without adjustable preload, they're usually made a little tight, and you run them a little bit, and then they settle in, they wear in, and they form a nice tight fit that lasts a long time, really maintenance free. There are some with preload. It's kind of like the clamps in the couplers. And they clamp to the top and bottom of the threads. Those are a little finickier, but those can last even longer because you have the ability to adjust them as they wear.
Oh, definitely.
And those are higher performance, I would say, than the spring-loaded brass ones that we all use. The split nuts, and they've got the top and bottom, right? Let's see, what else is there? Dynamite fixes tolerance issues. Yes, it does.
So is gunpowder.
Your foot won't hurt if you just chop off the foot. Yeah. Let's 3D printing checkers got another. Oh, sorry. Yeah. No. Good to see you. Okay. All right. Let's dive into the lead screw stuff. I'm going to share my screen.
Okay. Once it's shared, I can set it up.
Okay. How's this looking?
Oops.
We got a little fractal there.
Yeah, you're sharing the same screen. You're sharing your screen, so I'll just wait for you to get that cleaned up as well. You might have to minimize the video stream.
Minimize it? Yeah. I'm going to change one thing. I'm actually going to do. This is my first time using the screen sharing on here. I'm going to say application window here. There we go. How's that look?
I think it's showing it. Okay, add to stream.
You can see Inventor.
There we go.
All right. So here's a model of a lead screw motor that I made for working on in my assemblies of printers. And this one is using a TR8x8 lead screw because this is what's usually in those sorts of motors. Now, this is going to make my computer speed up a little bit. Maybe you're hearing the fans in the background because there's a lot of geometry going on in this thread. Yeah, let's go look at a top view here. So in a top view, you'll notice you've got this trademark 4 start. You've got 1, 2, 3, 4 threads intersecting this top cut cone. You can see them. Just look straight down, top down on a screw, and that's how you can know and count how many starts you got. Just pick one and go around it. All right. That's a lot easier than looking at it from the side. You know, if you're looking at this, it's like, how many starts do I have? I don't know. So here's something interesting about rigid nuts. At first, when you get a printer and the nut and the lead screw are not quite fitted to each other yet, they're both fresh off the machine, and they're brand new, and they've got a little bit of wearing in to do. Let's see. Only one of the threads, maybe 2, and possibly 3, but not all 4, are going to be riding on each other. This is contact-wise what it actually looks like, because you know, one of the threads, the 4 threads, is going to have a burr on it in the nut or something. One of those is going to be sharing, or going to be taking the actual thrust from gravity. So contact-wise, this is what it's going to look like at first if your nut is real tightened down to the machine. If your nut is allowed to wiggle, like up and down and sideways, you might have 2 threads, and that might look like, gotta suppress 2 occurrences. It might look like this in terms of contact patches. You'll have 2 of them that ride up and down. Or it might look like, say, this here. Kind of weird, but really that's all the contact that's being had inside the nut to the screw surface itself. After it wears in, and maybe if you've got some oil or something and you've got films in there that take up the gap between everything, you'll get 3, maybe all 4 of them going. But at first, especially, really, you're only making contact on 1, 2, or 3 of the threads, not all 4. So it's like, what's that 4th one there for? Well, the reason we've got 4 threads going together like this is for load. If you've got like a traditional CNC machine and you're routing things, that's kind of what these lead screws were designed for, right? They're for moving heavy loads pretty precisely, and they need to be very rigid against that sort of sideways shock. In that sort of situation, you're going to need all 4 of those screw surfaces, because it's going to be pushing up and down and changing direction, and all those loads are going to be pretty heavy, really, compared to the very, very tiny gravity loads that we see on our lead screws and 3D printers. So for us, it's kind of overkill. Really, if you could get a 3D printer with, if you could get a 3D printer lead screw made with just 1 of these threads, there.
So with just 1 thread, that would be optimal?
It would perform pretty much exactly the same.
Okay.
Because it's got the same pitch, it's got the same lead. It's just really stretched and spread out. Now, keep in mind, that's not the same as this guy here. So this is a TR8x2 lead screw. This guy, I'm zooming in on here, is steep. So you see how these threads are? This is only a single thread. I'll show you the top, so believe me. You can count, there's only 1 intersection, 1 thread. that has the same amount of contact as this guy, but it's a much shallower angle. See how that works?
Yep.
Really, for our 3D printers, where we don't need all this load capacity, we really don't need a 4-start lead screw. Actually, we're better served with the higher precision of a single start. So I usually tend to recommend these TR8x2s for most printers. And there are some specific reasons as to why, but just in general, the concept of trading speed for precision. On the Z-axis, what we want is precision. So we're going to usually take the trade-off of going for a single start instead of a multi-start, which lowers your precision but increases your speed.
Now that makes sense. Because, I mean, whenever we're designing anything, we want it to be at least the tolerances to be precise as we can get.
Mm-hmm. So, hang on. Let's see. Did I stop screen sharing there? Okay, I've got a chat here from Bob Carnes. He says monkey and tripod would say otherwise.
Yeah, that was the cutting off the foot.
I'm not sure what that's in response to. Let me know.
That was cutting off of the foot.
Mm-hmm.
Because both of them have been amputated at the foot.
So. Oh. Got it. I thought that was about like are these like lead screw companies who are, you know, not recommending what I'm recommending? Like, that like it's like a monkey and tripod. That would be a pretty weird name for like a machine shop or something. But okay, right? Like that's where my mind went.
Yeah, no, Tripod Garage and Monkey. Monkey Makes 01, I think is their handles on Twitter, are both, you know, don't have feet, but lost their foot. So
okay. Deininger.
Now, when we're going with these 1-start lead screws, is there changing that has to be done in the firmware? Yes or no?
There is, and I'll talk about that in a second here, because yeah, that's pretty important. You can't just slap one of these lead screws in for the other, expect it to work. There will be a stretching or shrinking of that axis, and it's not going to work. You do need to update it in your firmware. D in the chat is saying that's why I use 0.8 degree motors and single start. Yes, that's even awesomer. So let's dive into the nitty-gritty details of steps per millimeter. So whole step distance is something that I talk about a lot in lead screw resolution. So the stepper motors that we use for these printers are usually 200 steps per revolution. That's just the easiest to make and easiest to wind in this NEMA 17. It's just a bulk commodity. 200 step per revolution. NEMA 17 motors are everywhere. They're used for all sorts of things, and engineers can just grab them from any old place and drop them in their CAD models and order them from any old place, and they all work kind of interchangeably for things. You know, they've got spec sheets and whatever. But so 200 steps per revolution is the most common. You can also get other variants. You've got 48 steps per revolution. You've got 400 steps per revolution. 400 steps per revolution is pretty cool. I've got one of those that I use for the extruder on my console sitting behind me, which is, you can't see it. There. See the aluminum?
Kind of hard to see it. Yeah.
Mid rebuild, but
okay.
Get them going. That's the silent console. So I wanted more resolution for my extruder, but I didn't want to go with a geared extruder because those add a little bit of click, 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 click every time the teeth mesh disengage. You know, you're driving and then you've got a retraction, it'll click here, click. I didn't want that. So instead, I just use a double resolution motor, which should give me a little bit of extra resolution edge without having the noise that a geared extruder could provide. I know that's really nitpicking, but this machine was really, really quiet. Like I was running its drivers in Stealth Chop, the original Stealth Chop. You know, the one that's supposed to have really low torque. It was a really light Delta, expensive fans too. But anyway, so if you've got a lead screw that covers 8 millimeters in one revolution, because you've got 2 millimeters between threads, but you've got 4 threads. Remember how there were 4 of them stacked in a row?
Yep.
By the time it spins around once and gets up to the next point, 8 millimeters has passed. If you take that one revolution and you divide it by 200, the number of steps in a normal motor, you find that one step in that motor has traversed 0.04 millimeters on that axis, which is pretty precise, man. 40 microns, that's pretty cool. Microstepping can reliably hold positions much less than that, so that's really cool. However, if you use a single start lead screw in that 200 step per revolution motor, and you do the math, you say, okay, you've got a 2 millimeter lead and pitch, because it's a single start, but the same thing. Divided by 200, well, 1/100th of a millimeter, 0.01 millimeters, that's 10 microns, is your whole step distance. That has the very slight but sometimes noticeable advantage of being a little bit more repeatable in certain situations. It doesn't show up a whole lot, but if it does, it's just one nicer thing to be able to rule out on the machine. So if you've got those single start lead screws and you pair them with a 200 step per revolution motor or more, a 400 step per revolution motor, like Dee was saying, any layer height that can be expressed in 2 decimal places is fair game. It'll land on the exact same microstep every time, and it tends to be just a little bit more repeatable. Your layered registration might improve a little bit.
Okay.
For 400 step per revolution motors, they're 0.8 degree motors. That's half of that. It's 5 microns is the distance traversed by the axis. And so you can use any layer height that's 5 microns, 10 microns, 15 microns, 20 microns.
You can get some really crazy resolution with something like that.
Yeah, you could if you wanted. I don't know. Most extrusion systems can't dispense. They can't meter out that tiny amount at a time. But 3D Medic Vince is saying he put a single start as Ender 5 because in 4 start, the bed would drop easily and the single start holds it in place. Yes, and that's the other thing. Ooh, cool little plug in there. I'm going to share my screen again because this will explain why that is the case. So let's go back to here. A lead screw is just a clever little application of a ramp. You take a ramp and you wrap it around a pole. If you were to unwind it, unwrap it, it would just be a straight, very gentle ramp. This TR8x2 would be very, very gentle. Now, the coefficient of friction, and if you guys know what I'm talking about, you'll know how this works, but can be very simply related to a slope. You can relate the quantities of the normal force and the force that's projected and attempting to pull it down the ramp. And if you take the inverse tangent of that ratio, you can find your angle here. So coefficients of friction are related to angles, what I'm trying to say. In a lead screw with a very steep or comparatively steep, I'm going to turn all these off so you can see what I'm dealing with here. With a comparatively steep angle, this is kind of what the ramp you're dealing with looks like. Imagine if it were a straight ramp. That's actually kind of steep up and down. A lot of substances, if you let them sit on a steel ramp of that angle, would slide down on their own weight. And guess what? That's exactly what these nuts are doing. So if you want to ensure that a nut won't be able to slide down that ramp, in other words, turn the lead screw under its own weight, you can choose a steeper angle like this, or shallower angle. The other thing you can do is just increase the friction. So you can increase the preload between the two, jam something up against the bottom edge, jam something down against the bottom edge, either a spring-loaded or like a hard, like a...
You mean like a backlash nut?
What's that?
You mean like a backlash nut?
Yeah, like an anti-backlash nut. That can add more friction and just lock you in place. So even on a steep angle like this, it's not going to slide down the incline, so to speak. Remember that incline that's wrapped around this pole. So that's the other reason I really like these. You don't even really need anti-backlash hardware in order to just keep from sliding down when the power's off. The angle is so steep that if you take the tangent of that angle, you can find that your coefficient of friction would have to be super duper duper low for something to slide down on its own. Now, ball screws with a angle, helix angle is what it's called, that's this shallow, would probably be able to slide down under their own weight. That's because ball screws, remember, have rolling friction, and as such, their static friction is very, very, very low. Yeah. So well lubricated ball screw, even a shallow one like this, would often be able to slide down under its own weight. Forget about it. They totally would slide down under their own weight. So this is where holding torque comes into play. During a print, when the motors are energized, and assuming they stay energized, it's not going to slide down under its own weight because the motor's holding it there. This is more something we talk about like when the print ends. And you want to make sure that it doesn't like slide down on its own. Or if you've got a machine with 2 lead screws, you've got one over here, you've got one over here, like Prusa's, right? You want to make sure the 2 sides stay synchronized. Having it slide down under its own weight, one side might slide more than the other, and they can get out of sync. So yeah, that's something to deal with that there. So
one thing I've been thinking of is that, you know, when designing a printer, I was going to ask you another question, because this is kind of like a little bit more down your neck of the road. Is there a difference between T and V slot when it comes to setting up a printer? And would that decide, would you have to change some of the characteristics? Like if it was, say, if you wanted to use T instead of using V?
So there's really only one main difference between T slot and V slot, aside from, you know, maybe stiffness is maybe a little different. You can look at the second moments of the area on that. Their stiffness is really pretty comparable. The only main real difference, because V slot was designed to be a drop-in for T slot, is that V slot has that, you know, trapezoid, 45-degree, whatever. I think it's 45. That,
yeah, it's 45.
Like polycarbonate or Delrin wheels are supposed to be able to run in and use the V slot beam, the structural element, as your linear motion element. And that's pretty cool. It's kind of like using, I've got some printers behind me, maybe you can see these guys. These are CubeX printers from 3D Systems. You guys remember those? Chipped filament and all that. Those use big steel round rods as their linear motion components. Not only are they linear motion components, but they're also the structural components. That's pretty cool. You know, you're making it do a double duty, so your part count is a little lower. It's kind of the same idea as using V-slot, both as your structural component and your linear motion component. You have the wheels rolling right in the structural element, and you know, you get a linear motion element out of it for free. Cool. Other than the slight profile difference, they're really pretty much the same. Often T-slot will hold like a hammer nut just a little bit better because of the way that the T is designed. It's got a little bit more spring to it. But I mean, these are minor little tiny details. The V-slot works well enough for that, especially if you've got conventional T-nuts, the ones that have to slide in from the end. Those hold really well. You won't really see much of a difference structurally between V-slot and T-slot. They're pretty much drop-in.
Yeah, because the reason I'm asking the question, and this is going to sound kind of a little different because Barrett thinks I'm talking about something else, but one of our friends, Colin, he actually took a Bear model and made it out of T-slot instead of making it out of V-slot, thinking there shouldn't be that much of a difference.
Yeah, should work. So remind me, the Bear, is that using round?
The Bear is taking a Prusa build, and instead of you know how Prusa has that just that one center mass over for the Cartesian, and it's very thin. They're just saying put up V slot and you can make it a little taller also.
Yeah, use the aluminum extrusion for the frame instead of like a cut MDF or acrylic piece or all that.
Yeah.
So, but I mean, motion system wise, most Bear models that I've seen use either round rods or linear rails. I haven't seen a whole lot of Bear ones using V wheels in V slot. Yeah. So if you're using wheels in V slot as your motion system, yeah, obviously it's got to be V slot. You don't want to run the wheels in T slot. It's not as good. But if you're using other dedicated linear motion components like linear rods, linear rails, then V slot, T slot doesn't matter. You're just using it as a framing element, a structural element. You use T slot, use whatever's cheapest and straight instead.
Yeah, I'm thinking if I'm going to build a printer, I was looking at going linear rails all the way.
I am really partial to linear rails. I think they're a really nice way of doing things in the 3D printer world.
Plus, the speed you can get off of them is really nice too.
Mm-hmm.
You're not constrained to the speed of the belts can run. Mm-hmm. Well, I guess you're a little concerned to the belts, but less friction for them to move back and forth, minus the wheels, because the wheels would add friction.
Wheels do add a bit of friction. That comes with the 45-degree profile that they're on. Tangential speeds at the top and bottom of the slot are different because the radius is different there. So you've got a little bit of wheel scrubbing as it rotates across the surface. It's not just a straight roll. It's got like kind of a scrubbing motion. It doesn't add a lot of wear, a lot of friction, but it does add up over time. Yeah, it does add more friction than just like a straight rolling element, or ball bearings in a Gothic arch. Now, I would like to see Gothic arch T-slot. That would be
Gothic
cool.
Arch T-slot?
Yeah, I'll share my screen if I can find.
Yeah, because you got me a little concerned. Well, like never heard of the term for that type of slot.
Okay, yeah, perfect. Here, I'm going to share my screen here. So, a Gothic arch is a type of bearing raceway.
Okay, I'm going to zoom in a little bit more so we can see it clearly.
Yeah, here, I'm actually going to zoom in on mine. No.
Oh, they want us to see an ad.
Yeah, here we go. This is the meat and potatoes of come on, it's frozen. Come on, there. You've got, instead of that scrubbing motion, you've got point contact.
Oh, okay.
So I think this would be really cool on V slot. Obviously, you're not going to be able to get away with just straight cut wheels. You'll need wheels with curves on them, and it'll be more expensive, and they won't last as long because you'll have point contacts, and that'll wear them down. But it'll be cool for a while.
Yeah.
D mentioned his son designs machines in North Carolina that have 1.2 million steps per revolution. Yes. So here's the difference between observed angular precision and commanded angular precision. So it turns out it's a lot easier to make a structure that just observes the angular position of something than it is to impose an angular position on something. If you want a rotor to be able to, say, a million steps per revolution, you need such fine, tiny wires going around in there. You can't cram electricity through things like that, at least now with modern manufacturing techniques. It'd be pretty nuts. But there are loads of ways to make passive elements that you just look at that show you what the angles are. What we typically use, I'll show you how this works. Trying to find a really good picture.
Sorry, I'm just trying to do something here, and videos are kicking up on my screen here, so I do apologize for the background noise, people.
Here we go, a gray code. Here's the picture I'm looking for. Come on. All right, I'm going to share my screen now that I've found this.
Okay. It'll automatically should share.
Mm-hmm.
I'll have to issue it.
There we go.
Okay.
Is that working?
Yeah, just sure. There you go.
Okay, so encoders like this, say in mouse scroll wheels, are really easy to do. A little bit more difficult is something like this. You're usually using a gray code, which is kind of like binary, both a couple inversions in there. And this basically lets you double your precision for every additional layer you add out. So you've got this inner layer, see how it's half black, half white? You put a photo sensor somewhere on here, say up at the top here. And if it's white, you know you're in this half of the wheel. And if it's black, you know you're in this half of the wheel. Okay, there you go, another layer out. Now you've got a black and a white and a white and a black. And you put another photo sensor up here. Oh, now you can tell which quarter you're in. You've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, something like 14 here. That's 2 to the 14. And this would be something like 16,000 positions just from pointing optical sensors at this funky little printed pattern. 16,000 steps per revolution. That's pretty cool.
Wow.
Yeah. Now, if you were to try to make a motor with this sort of resolution, it would be darn near impossible because you'd have to have like mechanical teeth or some sort of physical implementation of or physical embodiment of this level of detail. That's hard to do. It's much easier to observe angular position than to try and impose it on a system. So, hope that makes sense. So, a lot of servos can have really like crazy high resolutions. We're working with some. I think they're like, we have them at like 500,000 steps per revolution is what we were using on the, the ones on the BAP, but they went to like 2 million or something like that we would never use. It's like,
yeah. Speaking of the BAP, how's the BAP coming along?
Not much progress on that recently. I've just been so swamped down here.
Understandable.
Yeah, we'll get it going. That project is something I really want to see through to the end because it's so cool.
I'd love to see it operating and just see it pump out that filament like no man's land.
The thing could fly so fast.
But we're in strange times right now. What can we say?
Mm-hmm. So it looks like we still got 5 people watching. I wonder, so a roll call. Anybody else got questions or things you want me to deal with? Otherwise, I'll dive into belts and more about the.
Well, I think we should go into the Vroom Troom that Bear was asking. Yeah, where they went to belts on Z-Rod because you did say you wanted to get into that.
Yeah, let's dive into that then. So, there are 2 aspects to. There are two features we're interested in the Z positioning of Z linear motion element. You've got your behavior in the axis, right? You've got like resolution or repeatability, right, in the axis, and then you've got side effects like lateral play, and you've got noise and other things that are not directly related to how well it's moving the thing directly in the axis. Lead screws are pretty great at moving things in the axis, but if they're bent, they also have the side effect of adding Z-wobble to your prints. Belts, because they're flexible, don't have really any ability to constrain something, to add a constraint horizontally to your Z moving platform. Because of that, you don't really get Z-wobble with belts on your Z motion system. I mean, now it's not all great though, because belts obviously, well, maybe I shouldn't say obviously. I will now say why it's obvious to me, and now it will be obvious to everybody else if it's not already. It probably is, but why belts aren't the be-all, end-all for Z motion systems. So belts have a lower static stiffness than a lead screw does. So a lead screw is a rigid element. You have solid steel down there, and when you push on it, there's not much bounce or compression or flexing or anything going on in the system. If you have a Z lead screw setup, and you do a little Z hop, and you stop, it will land on the nut surfaces on the lead screw's thread and just sit there because it hit a rigid stop, and it will not bounce. It won't do any of that. The Hooke's law is essentially the stiffness constant of the system is very high. Belts are a bit lower, especially if they're not tensioned super high. And if you're using cheap belts, you can go in for a Z hop, and it might settle a little bit, and it'll give you a little bit of a wiggle when you're coming out of a corner. Let's see what else. My main beef with belts, though, is resolution. So when you're moving a belt with a pulley, the circumference of the pulley in one turn is the main thing we're interested in. If you've got a 20-tooth GT2 pulley and it's a 2mm pitch on the teeth and it spins one revolution, 20 to 40 millimeters have passed. That's a lot more than like 8 in the case of a 4-start lead screw. And I like single start lead screws with the 2mm pass. 42 millimeters. The belt has 20 times less precision, or 1/20th the precision. Is that an issue? Sometimes yes, sometimes no. Deltas make it work really well. With micro stepping, belts can work great, but they do have the potential drawback of maybe not giving you the positioning accuracy that you're looking for, like really low layer heights or really precise precise models. Now, that's operating under the assumption that it is directly coupled to the motor. It's not geared. A lot of people nowadays are driving them with worm gears or with like planetary gear reducers, that sort of thing. The weight on the axis preloads the whole drivetrain, so any slop in the gears is taken up. It's not really an issue. They're sitting on one side of the gear teeth. So that works. If you've got a torque multiplier like that, and a resolution multiplier like that, your motor will be able to move the axis with a potentially comparable or maybe even better precision than a lead screw would be. However, you've got to take into account the step nature of the teeth. Sometimes you'll have a couple like 2mm periodicity waveforms on the side of the print if your belt tooth profile and the tooth profile and the drive pulley is not exactly matched up. So if you're going to the trouble of making a nice printer with belt-driven Z-axis and you're doing a gear reduction in there, yeah, get some nice belts, get some nice pulleys, get the genuine OGE gate stuff. You won't regret it because those teeth profiles will mesh really well and you'll get a really nice
yeah, because thinking to, when you mentioned the pulley idea, the other thing that I'm worrying about is stretch with gravity. And with the amount of time that, say your printer head is up here, your bed's down here, I would think with gravity and over time, that would actually stretch out the belt and not allow the belt to function as well.
A little bit, although thankfully with modern belt materials, I mean, usually our belts are fiberglass or Kevlar. They've got polyester cords in them. They're not just rubber bands. They've got something in them. Even steel is okay for this, although steel does tend to creep a little bit over time. It's pretty minimal.
Okay.
It is a thing, and it's measurable. It's repeatable. Like you can document it, but it's very small. And if you maintain your machine on a regular basis, it won't usually be enough of an issue to cause serious print issues. Usually, other things are acting up a lot more than those. So it's a thing, but it's not a serious thing. That makes sense.
So, just to say, Barrett just posted this right now. He says that's why the Tron uses reinforced belts.
Mm-hmm. Yep. The Trudon, yeah, I think they use fiber. glass, although it could be Kevlar. I don't know. I've been trying to get my hands on some carbon reinforced Gates belts because they have even higher stiffnesses. But yeah, we're kind of splitting hairs. You can just make the belts wider too, wider, thicker belts.
Yeah, that
If
would
a
work
belt
too.
is double width, it's double the stiffness. It hooks long. Just model it as a simple spring. What's my deflection going to be? You can calculate all that stuff.
So, with everything that's happened, how do you feel about Murph and Earth now going virtual? What were your thoughts on it?
Well, I think it had to happen. 3D printing llama's got a good point here. Yes.
Yeah.
3D parts will deform more over time than the belt stretch. Yeah. If we're being realistic here, the belts are not going to be the bottleneck in the system. They're professionally made with really high grade materials and usually are janky cantilevered plastic pieces in a heated lac enclosure, and they're going to be the weak link usually, unless you've got like an all metal setup and you've got machine parts all over the place, water jet, whatever. Plastic parts are going to be more subject to creep than the belts will be. So, yeah, really, engineering has a lot of chasing down bottlenecks and running them out of the system. When you're trying to improve or optimize the system, you look for what the next nearest thing is that's hurting your bottom line, and you say, oh, I'm going to tackle that one, and you improve it up till the point where it's not the thing that's limiting your performance anymore. Like if you were to take a Mustang and give it 2,000 horsepower, but you left plain old stock tires on there with ordinary roadworthy rubber compound, not wrinkle walls, not like sticky slicks or anything, it wouldn't be able to deliver that much power to the ground. The contact patch is too small, all that sort of stuff. In terms of acceleration, it's still going to be limited by its tires. And really, like a 700, 800 horsepower Mustang would accelerate at about the same maximum rate because the limiting factor in the system is your coefficient of friction on the ground. So you could take all that money that's going into the extra, 700, 800 to 2,000 horsepower. You could put that into just some nicer tires, and hey, you would actually get a lot more performance. Let's see, what's another example? That's one I use for car guys. Jake from State Farm building a Warren with 9mm belts. Yes, that's a good way to go.
And pulley from the Z country.
Mm-hmm. Let's see, what else? Oh, for computer people. A lot of us are computer people. If you're to make a really nice computer, you're building a desktop, you've got SSDs, you've got like Intel Optane memory, you've got a really sweet graphics card, you've got a great processor with a lot of cores, but you give it 2 gigabytes of RAM. It's going to be a struggle on a daily basis. It's going to run hard because the RAM is going to be the constant bottleneck. All the processes that are running through there are going to have to be fetching stuff from the cache paging and back to the memory, which granted it's SSDs, so they'll be fast, but they're not nearly as fast as RAM. That's going to be the bottleneck in the performance of the system.
Well, actually, your SSD could be considered a bottleneck of your performance also if you're not running, if you have the option to run, what is it called? The hard drive on chip. What is it? It's still an SSD, but it's connected directly into the motherboard. Oh, N2?
M.2.
M.2 yeah.
Yeah, that's what Optane is. That stuff is great.
Yeah. Fortunately, my board won't accept that. My board's too old.
Mm-hmm. So, yeah, that's basically how I think about this. You find the bottleneck and you address it. If the amount of belt stretch that we're getting is like a magnitude below, printed part deflection, maybe the printed parts are the thing you should look at before worrying about the belts, right?
Yeah.
Yeah,
because personally, like where I'm planning on going, I want to build myself. I want to take that CR10 and try to disassemble it and build it into something else. Because I noticed ghosting is a major problem with that. So to address ghosting, you'd have to have your Z flat, your Z bed not the Y not to move.
Mm-hmm.
So maybe turning it into a hypercube would give me the speed I'm looking for, but also would take away any of the Z ghosting or any of the Y ghosting or any of those extra little things that the CR10 tends to do with it being the style printer it is.
Mm-hmm. Yeah, I think it's kind of a minimal build. It doesn't have enough components for like a full cube frame, but you can scavenge that sort of stuff and convert it into that. A lot of people do that sort of thing. It's a good starting point. You've got motors, you've got lead screws, you've got belts, wires, all that. Ooh, use explosives. How about that metric hammer you were talking about earlier?
Everything's explosive.
Metric chainsaw. They make metric. They probably actually do make metric chainsaws.
Probably they do. But it's just like it's just the ghosting I'm getting, and it's just driving me up the wall with the with why. Because I mean, I know the CR10 you can run that thing as a beast. I know that I can get it up to, I believe it's 100 on the X. But I noticed that also when I run at 100, I get ghosting like no tomorrow on the Y. So
yeah, so let's discuss ghosting. Ghosting or ringing. Ghosting is a reference to the appearance of the artifacts that it makes, and ringing is a reference to the physical nature of what's going on in the printer. By ringing, I mean every time you hit a corner, there's a force, a deflection spike, and everything deflects from its natural position, and there's going to be some oscillation as everything settles back into its natural state and vibrations dissipate. So you've got a couple different features to look at when we're trying to analyze ghosting. One, you've got the specific stiffness of the system, not the absolute stiffness, but the specific stiffness. Now, for science and engineering people, specific, when you put that in front of a quantity, it means divided by mass. These are inertial machines. Basically, everything you're fighting is the mass of the machine itself. The enemy here is its own movement. That's what's generating all the ringing.
The inertia.
Every time you try and make that change direction real quick and slam into a corner and zip out the other side, all those quick direction changes excite vibrations in the frame and in the belts and everything. So that's what we have to analyze. You have to analyze the specific stiffness of all the components. Now you've got frame bits. You've got your Z towers and you've got the thing on the top. If your x-axis is zipping back and forth really, really quick, you could get a little bit of this conceivably, right?
Mm-hmm.
Maybe more at the top than at the bottom. Okay, that's one thing you could look at. Usually not much of an issue nowadays, but it was back in the old days on like the I2 Mendels. They were pretty susceptible to that sort of issue. You'd hit the resonant frequency of the frame because they didn't have any bracing in that. They would go doing, 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 doing.
Oh, really?
And yeah, because they were all threaded rod and they didn't have any bracing in that direction. So people started putting printed V braces and things in to solidify that. They would do this. Yeah.
Oh, geez.
What else is there? You've got the stiffness of the belts, whatever tension they're at currently, and then the forces that are excited, or the forces that are imposed on them by the commanded accelerations and decelerations. Those are going to attempt to deform the belts, right? And the belts are going to bounce. Then you've got the damping of all the things involved. The frames are often pretty stiff. If they're all like metal, they don't damp a whole lot. But if you've got printed parts, those damp a lot more. If you've got belt rubber, damps pretty quickly. Vibrations in those kind of die out. If you've got really high quality linear ball bearings, those don't eat up much energy in friction. They just boing, 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 they'll bounce back and forth. If you have like polymer sliders, like I guess dryland bushings, the friction actually will eat up a little bit of kinetic energy in the ringing and will damp it. That sort of thing. So there's a whole bunch of engineering elements you got to look at all together. You've got the damping, you've got oscillation, you've got frequencies, you've got specific stiffness is the main one. That's what I like to hammer on. And then you've got what you're trying to command that to do. Accelerations, jerk. So accelerations are directly proportional to force. If you double the amount of acceleration that you're commanding the printer to do, say in your y-axis, which is giving you the most ringing, you're going to see double the forces on that belt, and all other things being equal, which they might roughly be equal, you're probably going to see double the amount of energy contained in the oscillation. Now, if that translates to like literally double the ghosting visible, I don't know, but you'll have double the energy. Then you've got acceleration is directly proportional to the forces involved. Then you've got the time derivative of the force, the time derivative of the acceleration. If you just let the printer start and stop accelerating instantly, that poor belt is going to have a lot of work cut out for it, because it's trucking along at a constant velocity, say, and then it's like, oh no, you got to start accelerating. All of a sudden the motor starts accelerating. That poor belt has had basically no net force on it, and suddenly there's a net force. That spike in force is, you can analyze these with all sorts of nifty tools like fast Fourier transforms, and engineers love to get into those details. I kind of do, but other engineers really love to get into those details. And that is a step function that can excite vibrations in the system very nastily. So really what you want to do is you want to have acceleration start gradually, like it ramps up into the acceleration. That's S-curve acceleration. So that's got a limited jerk, and I'm not talking the 3D printer type of jerk. I'm talking the actual like jerk, like the time derivative of acceleration, which is the time derivative of velocity, which is the time derivative of position. So this is in units of distance per time cubed, which is a strange unit to have. We don't deal with it a whole lot in everyday situations, but engineers deal with this from time to time when we're trying to make things feel smooth. For example, you've got railways. Railway designers deal with jerk. They've got to carefully mesh. You can't just start into a curve all of a sudden. You've got to gradually ease into it, because if you're just going straight and you gradually, or you sharply hit a corner, they're tangent. It's not like there's a disjoint there, but it just starts curving all of a sudden. That train is going to slam everybody inside all of a sudden because the force just started. That's not comfortable. So certain engineering disciplines deal with this quite a bit. Jerk being the time derivative of acceleration. So unfortunately, to muddy the waters, we've got another thing called jerk on our hands, and it's not actual like jerk. I'm just checking this here. So Marlin and maybe some other printer firmwares from a little while back use a variable called jerk that kind of approximates what real jerk, like time derivative acceleration, does, except it's a little bit of shortcut. It's the maximum velocity change instantaneously allowed when coming into and out of a corner, meaning it'll bypass the acceleration phase entirely. It'll just jump from stationary up to a specified speed, or from down in that direction to up. That is really hard on the system. That's not a step function. That's an impulse function. So that, if everything were perfectly infinitely rigid, that would impart an infinite but infinitely thin spike of force to the system. Impulse functions are great ways for engineers to find out what in a machine rattles. Unfortunately, that's not the goal in printing. We want everything to be smooth. But there are downsides if you're not using jerk and you have to slow down completely to a stop in every corner and start out of every corner. Print times are longer, but mainly it's an extrusion thing. Your extruder's got to completely stop, and oozing happens, and then it's got to start back up again. So you'll see, this is what Linear Advance was designed to combat. You'll see kind of a bulging coming into the corner, and then a starved area coming out of it. So jerk helps extrusion consistency. It keeps flow rate more constant, but it hurts the motion system. It's an impulse function, not just step function, but an impulse function that excites all sorts of nasty vibrations in the frame, in the belts, in the motion system, even in the motors. You've got rotor deflection in the motors. And all that's linked together and coupled together, and you've got all sorts of crazy equations that can model this stuff. But so, yeah, that's basically the lowdown of it.
That makes sense. I mean, I'm thinking to myself with also, I guess we would also now. It's going to sound a little weird, but it actually probably fits into that. So, because we're calculating weight, the speed of the wheel. So let's take the CR10 for instance. It uses a bed. Bed moves left, front and forward, back and forward, I should say. Now, sometimes they have glass on them. Some guys have gone to not using glass anymore, using the flex plate.
Mm-hmm.
Now, would we have to take that into the equation to figure out, or like, is there a way that we would figure that out in firmware that we can actually put that in?
Not in firmware. This is where we've got to use our the milkshake sitting inside our skulls that do math magically. Our brains. This is where we use our brain power.
Yeah.
If you have like a stock CR10 and you wanted to put a glass plate on it or something, and it maybe increased by, increase the mass of that Y axis by a little bit, you could weigh it all, figure out how much extra it added. Say it added 10% more. So the total mass that's being slung around is 10% more than what it was. If you had previously found an acceleration setting that was all right, and like just what you were able to tolerate, you could say, all right, it's now going to weigh 10% more. I know that I'm going to need to keep the forces on the system equal. I'm going to need to step down my accelerations by 10%, or really 9.090909%. Divide it by 110%. And that will give you your new acceleration that will keep the forces on the system equal to what they used to be.
Okay, so
you might want to do the same for jerk.
Okay, so you should actually recalculate this stuff if you're changing your whatever bed surface you're using, correct?
I do, but
okay,
most people don't. And you don't really need to. It's just a matter of like trade-off. What are you going for? Are you going for speed, or are you going for like super low ringing? I can't decide where on that spectrum, what you're concerned about, what you are looking for in that print. If you want no ringing, no ghosting at all, you can turn the speeds down, turn the accelerations down, which turns the forces down, turn the jerk down, which turns down the impulse function that's exciting everything in the motion system. And that will lower the forces on everything. Voila, you're going to have a lot smoother corners and no ringing and ghosting. But your prints are going to take super long. So, it's always a struggle against time.
Yeah, this is a trade-off. Either more time, better quality, or less time, not great quality.
Yeah, and people can find their own balance where they want to fall in that. Sometimes if I've got something I really just need to crank out and it's structural, it goes somewhere behind something, it'll never be seen by human eyes, but I want to get it done fast. Yeah, well, as long as I know I'm not asking the system to have so high of forces that the motors are going to skip steps or something, I'll maybe crank up the accelerations a little bit, and yeah, there'll be some ringing, but it's okay. It's part of fitting the process to the application. Whereas on the other hand, if I'm printing something that's going to be a display piece, people are going to be looking at it, analyzing it, handling it, kind of critiquing it, it's probably worth it to turn down those accelerations, turn down the forces, turn down the jerk or junction deviation, whatever you're using, and make the print quality around those corners come out a little better. And yeah, you get familiar with your numbers and what they work like for your printer. If you've got a heavier bed than most people and they recommend some settings for a certain model, you go, oh yeah, maybe I should turn those down a little bit because my bed is probably heavier than his is. You get a feel for what your machines are like, what they can tolerate, what they can safely handle, and you learn to adjust the settings accordingly.
Okay. Yeah, because I was just thinking to myself with my bed and just thinking about how weight would be thrown back and forth on it. Here's something of an interesting thought just kind of popped in my head, and this has more to do with how do I want to word this? Not resin print. I know 3D printing trucker said he's getting more into resin versus FDM.
Yeah,
What's your feel on resin versus FDM? Do you think we're at a point now where resin is the way to go now, or do you think we still got a lot more waiting in resin till it's at the point where it's like practical that everyone would be using it.
Man, I don't know. My specialty is in motion systems and motion control, and all informally, but I it's mostly just self-taught. A lot of reading. The a little bit of thermoplastics I picked up here and there, but resin is a whole nother ball game. It's more controlled by chemical and microfluidics variables than like normal Newtonian physics, like I'm used to. Like motion x's double the weight doubles the forces, half the acceleration, forces stay the same. Yay, I just used an equation. Yeah, that's all easy. Microfluidics is it's a whole like other
Different
thing.
ball game. Yeah,
Understandable. I don't have a resin printer yet in my apartment here. That would probably not go over too well with my honey. I'm getting married in 28 days.
Congratulations, man.
Thank you. I'm so excited. So we'll be here for about a year. Probably then move out, hopefully get a house if everything else works well. And then I'll have a separate room, and then I'll get a resin printer there. Yeah. In an apartment, this small, 2-bedroom, we're fitting 2 people's worth of stuff into this. Probably not a good idea to be running a resin printer in here. It's a little bit close and be kind of stinky.
I think
so. I'm waiting on that. I've got enough to keep my hands full already.
As my friend calls it, you have to have the female approval rating.
That's right.
Happy life, happy wife.
Moving into here, yeah, happy wife, happy life. When I was moving into here, this was in my head the printer room. And my brother was like, "No, you can't call it the printer room because then she'll see it as like only printers go in there, and she'll be like, can't I have this room too?" It's the craft room, okay? It's the craft. It's not the printer room. It's the craft room. It's also my office, and actually, what do they call it? A multi-role space. That's what we're doing here. It's a multi-role space.
Yeah, like where I'm sitting right now is my studio / storage for all my gaming stuff.
Mm-hmm.
The other room is for the 3D printers and any other stuff I work on the side.
Yeah. So resin, I'll get into that soon in a bit. It's too cool not to, but
trust me, I want to play with resin, but in my house, there's no way to ventilate it properly. Yeah. That's what the one thing I worry about is ventilation. So
yeah, everybody is or should be concerned about that with resin. These are very chemically active compounds. They're designed to be. They have to polymerize. They have to cure when exposed to ultraviolet light. So they've got a certain amount of loose cannonness to these molecules. They're not totally stable. Like they're looking for ways to polymerize and oxidize and shed things, and they're kind of active. They're not stable in the sense that a cured resin print is stable, or a thermoplastic, or even like a thermoset plastic is stable. It's done. It's not really chemically active anymore. You'd have to hit it with a lot of energy to maybe like make it cross-link or heat it up to the point where it starts actually decomposing, like polyoxymethylene, Delrin, which turns into formaldehyde. but that's a separate thing. You have to go out of your way to make those misbehave. Resin is supposed to misbehave as part of how it
cures.
Like it's got to be chemically active, so it's gonna be stinky. Now there are compounds and things, additive stuff you can put in to help minimize that, and material science is in full swing in that department right now. Well, maybe not because of COVID right now, but that's a really hot research place right now. A lot of companies are working on materials. You've seen flexible 3D printable resins come out. You've seen tough. You've seen heat resistant ones. Like
I'm a little curious on the heat resistant ones, because I was thinking to myself, it would be nice to print a resin pet fang, like bent the pet fang out of resin that is heat resistant, and that way I can run 240 and not worry about melting the plastic I have around for the pet fang.
Right. Although keep in mind, since it's not a thermoplastic, once it hits that temperature, it might be more like breaking down than just melting and then re-solidifying again once it's slumped out of the heat. depends. You know, you can look that all up in the spec sheets. But the yeah, I'm not jumping on the resin train quite yet because it is still stinky, still sticky, still messy, still kind of toxic, and disposal is a little bit of a pain.
Yeah, especially if you live in an apartment.
Yeah, so not the right time, not the right place for me quite yet, but I'll hop on that train sooner or later. I will say this: there are a lot of advancements going on right now in the resin space, and with all the printers that are coming out for it, there's a lot of demand for companies to make good resins, and they're coming up with all sorts of cool stuff that has neat 3D properties. You know, less warping, better temperature resistance, more impact resistance, all sorts of neat functional stuff. Yes, they're unstable like most of us. That's right. I feel very much at home.
Yeah. Well, we're going to end it on this stop right here. So I want to thank everyone for tuning in. We'll plan another episode if need be. So, guys, thank you so much for tuning in. And where can everybody find you, Daniel?
You can find me on Twitter at Techie Fiddler, on Facebook, search for Techie Fiddler. I'm on Instagram at Techie Fiddler. Sensing a theme? That's my name for everything online. I'm on Reddit, although I don't use Reddit a whole lot, Techie Fiddler. So shoot me printer questions. I love talking about printers a little bit too much. So yeah, we'll chat about this stuff. If you got any questions, hit me up anytime. I love it.
And myself, thank you so much for watching. If you haven't already, hit the subscribe button. If you're not already subscribed, hopefully you found this informative, and maybe we'll make this whenever we can get Daniel together and me. We'll put out another episode. But
yeah, nice seeing you too, Nick 3D. This is good to get doing this again. I think virtual is kind of gonna be the new norm for a little while everybody's social distancing. You know, like Murph and Earth getting shut down. Virtual is going to be the name of the game for a little while.
Unfortunately, that's what it's going to be. Well, anyways, thank you so much for watching. And guys, if you got questions, forward them down in the comments. Daniel will periodically look at the video and may be able to answer some questions, or we can save it for another episode when we can get together again. And once again, congratulations to you, and
thank you.
You know, all the best to you in the future.
Yeah.
Thanks, everybody. Talk to you later.